Okay, so Professor Xun, please.
Okay, thank you very much for the introduction. My topic is an online approach for computing resource allocation and data placement in distributed edge cloud networks. I'm Shao Xun from Kitami Institute of Technology. We are, I think most of us are very familiar with the concept of edge computing. Here are two examples of how to use the mobile edge computing in everyday life. For example, for a data service-oriented scenario, the mobile users can download some contents from the base station. But actually, the contents are from some original content providers such as YouTube and Netflix. However, the users actually they download the contents from the edge servers. The edge cloud providers will catch the popular contents in the local base station to satisfy the demand of the mobile users. This is a very simple use case. In another use case, there are some, as we know, there are some mobile computing tasks that are energy consuming. Like the video analysis. For such kinds of tasks, the mobile devices can just upload the data to the nearby edge servers and offload the task to the mobile to the edge servers to save energy and reduce the processing time. So the edge computing, the use cases of edge computing is not very general. So let's take a further step and see. For example, in the near future, what should general edge computing service should like. This is a distributed edge cloud network architecture. It is a very popular architecture. The mobile carriers deploy the edge servers not in the base station. Either the core network, but the cloud run, the BPO pools between the core network and the base stations. So it's a very popular architecture of the post after the LTE time. So we can see in every edge computing data center, there are computing resources and storage, as well as the traditional resources. The provider also deploy some caching devices, and between the distributed data centers, there are high-speed internet. This is a user. So let's consider that what should a general edge request should like. In this request, it is very complicated compared with the simple content or task offloading request. In this request, this user requires two virtual machines of the red type. and the user wants to make the right type virtual machine to process data 1. And in the second line, the user also wants a green type virtual machine to process the data 01 and 04. We can see that in the system there is already data 01 located in the cache, but there is no 04. 04 is the original contents that the user wants to upload. So in this process, the mobile edge computing providers make money just like a traditional cloud computing provider by leasing the virtual machines to the end users. In this process, because the X2 plus link is a little expensive to transmit big data through these links. So the edge cloud provider will incur a cost for inter-cloud data transportation. Okay, now our problem is a little clear. From the standpoint of edge cloud computing provider, the objective is to make more revenue from leasing the virtual machines to the mobile users. Well, the providers will avoid using too much the inter data center links. So we see this is a general purpose edge computing architecture. So here is an example to see why this kind of architecture is necessary. We can see that if here is such kind of general edge computing service exists, a user, for example, this user can not only require the original contents, but can also this user can also requires processed contents. For example, this user may want the blue contents, make a transcoded blue contents and the compressed red contents, and finally combined contents in this pattern. So the general edge computing service will provide a lot of flexibility to users. We just say the basic problem in the standpoint of edge cloud provider, that is to maximize the revenue by carefully allocate the virtual machines and carefully collect and locate the cacheable data in a very clever way. And the main constraints, we have two main constraints. The first one is we cannot overuse the inter-cloud connection, inter-cloud links. And the second, it is a traditional constraint. When you allocate virtual machines to users, you should not exceed the capacity of your physical resource. Let's take a close look at this problem. In the problem formulation, we can see that it is to max the long-term revenue. That is, we do not. What we focus is not the revenue in some specific time, but it's we can sell more of the long-term revenue. The long-term revenue has a formulation of the time averaged formulation. The RT is the revenue from a time slot T. And we make summation of the revenue of all the time slots and divide it by the number of time slots. And the result is the long-term benefit of the provider. This is XAL is our decision variable. Given a request, a complicated request L, actually for distributed cloud provider, it has several resource allocation methods to satisfy a request, because he has a distributed several data centers. So the provider has to make a decision to from the available resource allocation strategies. The provider has to make a decision to choose one. This is what does XAL mean? And when making any resource allocation decision, the provider has to make sure the available resources is not overused. So this is again a time averaged formulation appears. It is to keep so CT is the intercloud data transportation cost in time slot T. So we make summation of the transportation cost in every time slot and divide it by the number of time slot, and we got the long-term transportation cost as time averaged constraint like C bar, and we have to make sure the time average cost is less than a specific value. So solving this problem is not that simple, because in our objective function and an important constraint, we have the time averaged formulations, and if we don't have the if we don't have any future knowledge, like what kind of request will come, how much resource is necessary, we cannot solve this problem efficiently. So in our approach, in the first step, we have to, because the objective function is coupled, there's coupling with the sequential time slots. So in the first time, first step, we have to decompose the coupling between the sequential time slots. So this is the solution we used. We introduced a virtual queue. It's not real queue, but it performs like a queue. At the start time, the queue is empty, and in each time slot, we observe a cost, data transportation cost CT, and we increase the queue with CT, and we decrease the queue with a constant L. This is the expected. This L is the same with this one. We want to keep the long-term transportation cost below L. So now we have a virtual queue like this. And for two sequential consecutive time slots, we compute the difference of the square of the queue, and we got Lyapunov drift. The Lyapunov drift has a upper bound actually. The upper bound is composed of a constant and one other term of the backlog of the queue. So with the help of the Lyapunov drift, this decoupling problem becomes simple. We just put one slot objective RT and the one other term of the queue. We just make summation of the two terms together, and now we got a new problem. In this problem, there is no coupling between the consecutive time slots. For every time slot, we focus on this new problem, and at last we can recover the solution of the original problem. Of course, it's not exactly the solution of the original problem, but this method ensures that we, in the last, we have a not bad solution with a provable gap to the original problem. And by far, we have decoupled the coupling between the time slots, but we still have another problem. That is how to make resource allocation decisions in this simpler problem. This is a summation of. This is a summary of the solution framework. We introduced the virtual queue in the beginning of every time slot. We update the virtual queue, and then it's another issue we have to overcome. That is, the time slot is a relatively long time, and during this time, the requests will arrive in any time, in arbitrary time. So we have to prepare an online computing resource allocation algorithms to deal with this problem. So to see why it is important. For example, in some time, there are two edge data centers, and a request like this. It requires two virtual machines of type 1, and to process data 4. Data 4 is here. If the provider receives this request, it has three choices to assemble all the virtual machines in location 1, assemble one virtual machine in each location, or do not accept this request. So if the first choice is adopted, the provider assembles all the virtual machines in location 1, then the provider obtains revenue 3 times 2 times 3, and incurs transportation cost 04 because there is 04 is not available in this site. Consider that right after this request, another request comes. It requires one virtual machines of type 2 to process data 3. And we can see that from the available resources, this request cannot be satisfied because the provider already run all the resources are running out. So the total benefit is like this: 3 times 2 times 3 minus cost. Actually, if the provider knows the future, that is to say, if the provider already has the knowledge that a request k+1 will come, it is better for the provider to just reject this request and just allocate virtual machines to this request. So this is the big problem, because you do not know the future knowledge. So you must keep the you must have some method to evaluate the value of the of each resource, and you must avoid the resource allocation in a biased manner to avoid running out some specific resource in very early stage. So actually, this if we model this problem with linear programming, we can see that we are facing a packing problem. When a new request comes, we have a new XAL. We cannot maximize this packing problem because the number of eggs increases with time. So we consider very interesting but very old but interesting trick, that is to build the covering problem corresponding to the packing problem. That's because the decision variables of the covering problem are corresponding to the constraints. The number of variable decision variable is increasing, but the number of constraints does not change. So instead of the packing problem, we consider covering problem, and we know the solution of the covering problem provides an upper bound of the original problem. So the tricky point is when we decide when we make the we use the dual variable. Here is beta. We use the dual variable as an evaluation, as a shadow price of the a certain resource. For each resource, there is a dual variable to show the how rare this resource is. So with this method, we got a competitive online algorithm. With this algorithm, yes, the tricky place is to keep the change. When we make some decision, we just keep the change of the packing problem and covering problem constant. And no matter how the request sequence is, our result is provable. And this is the performance of our algorithms. This is our opt is an unknown. Theoretically, optimal value is unknown because the problem is just too complicated, and there is no way to tell the real exactly the theoretical optimal value. How much is it? But solution obtained from our algorithm, we can ensure that it is a little worse than the theoretically optimal value, but it's not that bad. This is the simulation results to show the performance of the proposed method and the two benchmark methods. The x-axis is time, and the y-axis is the revenue. And we can see the proposed algorithm performs significantly better than the myopic methods. Okay, let me conclude my presentation. So we identified the requirements of a general edge computing system, and we propose an online approach that solves the joint optimization problem with performance guarantees. Thank you.
Thank you very much. So, is there any comment or question? Yes, I have a question. So you applied, you achieved a very good result. So and you applied your how can I say? You reduced the optimal packing problem to the constraint covering problem.
Yes.
Okay. So and how far your result? How close your result to the optimal result?
Okay. This actually it is 1 minus 1 in E. About around 60%.
Also very close to the optimal.
Yes, so we have to say it's not a bad solution. Yes.
Okay. Any other question or comment? Please.
正しい英語で全然知らないですけど、はい。多分よくわかります。
Thank you very much. I'm a system engineer for control system. I'm interested in using by this method for plant control system. Is it available?
Sorry? Plant control system? Plant control.
In order to control high speed rolling plant, for example, Shinkansen, how to control the Shinkansen traffic by computer, online real-time computer system. Yeah. So that such kind of online real-time system, your recommended present method is available or not. So I think it depends on the control cyclic time.
Yes.
For example, I need 5 milliseconds.
Yes.
This is available now.
Oh, okay, I see. Actually, it's not that process. Although we call it online approach, it's not that process. Actually, in this algorithm, we have two time scales with the cost-defined, cost-rate time scales. For example, this time scale, it is from tens of minutes to 1 hour or 2 hours. It is not that process. And if a request arrives, our server will make online decisions. So why I emphasize that this approach is online, because if we can make some assumption of the future knowledge, we can just get a perfect optimal solution.
I ask you, what is your goal by this approach?
Major application?
Yeah.
Okay. I see.
You said
Sorry.
general edge computing service.
It's not.
General edge computing service means not online real-time control service.
Yes, it's. I think the online concept is a little different from that in the control theories. I think we call it online because when we receive a request, we do not buffer this request. If we buffer this request, we can know we can have information of several requests, and we can make a perfect solution. But we say online here because we do not buffer requests.
Okay, so it's time for finish. So let's speak again.